Located 168,000 light-years from Earth, hidden within the Large Magellanic Cloud, the star WOH G64 has astonished scientists around the world. It is a place where reactions occur at dizzying speeds, turning it into one of the brightest stars in the universe, easily visible from immense distances. Along with this brilliance comes the release of colossal amounts of energy, generating power capable of altering the universe itself. WOH G64 is not only remarkable for its size, but for its terrifying strength. If it were to replace our Sun, it would engulf the planets within Mercury's orbit and expand all the way out to Saturn. Our Earth would be swallowed by the star's blazing red shadow, the sky would become a living hell, and surface temperatures would rise to levels incapable of sustaining life. So what created WOH G64 with such devastating power? A place where wonders are still waiting for us. Together we will lift the veil on these mysteries right now. Though it is hailed as the largest star ever known, WOH G64 is neither the brightest nor the heaviest. Its title of largest is entirely based on its physical diameter, a characteristic that makes it a unique cosmic wonder, challenging the very limits of how large a star can grow. According to research co-author Jaco van Loon from Kiel University in the UK, WOH G64 is estimated to have a mass approximately 25 to 40 times that of the Sun. This means that this star has likely existed for about 10 to 20 million years. If WOH G64 were to replace our Sun at the center of the solar system, the entire rocky planets and a significant portion of the gas giants would be swallowed whole, melting away and vanishing under extreme temperatures and pressures. The familiar solar system would be transformed into a chaotic, blazing inferno. The volume of WOH G64 is billions of times larger than that of the Sun, enough to house trillions of Earths inside it. But WOH G64 is not a solitary star. It is part of a remarkable stellar population. Deep within a dense region of young giant stars lies the Westerlund 1 cluster, home to WOH G64. This is one of the largest and most intense star clusters in our Milky Way, containing tens of thousands of stars, many of which are supergiants or extremely rare Wolf-Rayet stars. The high star density and intense radiation in Westerlund 1 have provided the perfect conditions for the birth of cosmic monsters like WOH G64. Locating and studying stars at such vast distances, especially those nestled in dense clusters and obscured by cosmic dust, has always been a massive challenge for astronomers. How is it possible for scientists to measure a colossal celestial body like this from thousands of light years away? what methods have been applied to unveil the mystery of WOH G64's true size? Astronomers first observed and cataloged the brightest stars in the sky, from Betelgeuse, the familiar red supergiant in the constellation Orion, to VY Canis Majoris, the star that held the size record for years, then UI Scuti, and now WOH G64, which has been identified as the largest star. This journey has reached a new height, challenging existing knowledge of the universe. Each of these stars pushes the boundaries of what we thought was possible in the universe, opening new horizons in astrophysics. To determine the size and characteristics of distant stars like WOH G64, astronomers must rely on indirect yet accurate methods. One such method is spectroscopy, which allows them to analyze the light emitted by WOH G64, thereby determining the star's chemical composition and temperature. Analyzing its brightness helps them understand more about the energy the star radiates, while the parallax method allows for an accurate calculation of the distance to the star. Although parallax is the most direct method of measuring distance to stars, for extremely distant stars like WOH G64, this effect becomes too small to measure accurately, forcing scientists to prioritize other indirect methods. These complex methods are made possible through the support of the most advanced telescope technology. The Hubble Space Telescope has provided detailed images and spectroscopic data, bypassing the distortion caused by Earth's atmosphere, giving a clearer view of distant celestial bodies. The giant telescope in Chile, with its 4 large telescopes working in unison, allows scientists to collect vast amounts of light and achieve unprecedented resolution. Recently, the James Webb Space Telescope, with its superior infrared capabilities, has opened a new era, allowing us to peer through thick clouds of cosmic dust, which were once the biggest obstacle to observing stars deep within star clusters. However, studying WOH G64 is no easy task. One of the greatest obstacles is cosmic dust obstruction. Dense star clusters like Westerlund 1 often contain vast amounts of interstellar dust and gas, absorbing and scattering light from the stars, making them appear dimmer and redder than they truly are. This complicates the process of determining their true brightness and surface temperature. Moreover, given the distances of thousands of light years, even a small error in estimation can lead to significant differences in calculating the actual size of the star. To obtain the most accurate estimate of WOH G64's true size, scientists not only rely on observational data, but also have to combine them with multiple complex stellar evolution models. It is these challenges that have driven the relentless advancement of astronomy. And every time a mystery is unraveled, we are left in even greater awe of the power and intensity of the colossal nuclear reactors in the universe. As we explore WOH G64, the immense power this star possesses is an undeniable factor. This power lies not only in its size, but also in the way it burns energy, generating light and extreme temperatures, influencing the surrounding environment and even affecting other stars within the Westerlund 1 cluster. A staggering truth is revealed. Inside its atmospheric shell is an energy machine of unimaginable destruction. WOH G64 isn't just the largest celestial body. It is a colossal nuclear reactor operating at an intensity that our sun could only dream of. At the core of WOH G64, where temperatures soar to tens of millions of degrees Kelvin, nuclear fusion occurs at a furious pace. Initially, like all stars, hydrogen is converted into helium, releasing an enormous amount of energy. This energy not only makes WOH G64 shine, but also creates outward pressure that counters the force of gravity, preventing the star from collapsing. But with its immense mass and pressure, WOH G64 quickly advances in the fusion process. As hydrogen depletes at its core, the star begins to fuse helium into carbon and oxygen. This process continues with heavier elements like silicon, ultimately creating iron. Each stage of fusion releases a colossal amount of energy, maintaining a balance between the outward pressure and inward gravitational force. It is precisely these fusion reactions that give WOH G64 its incredible fuel consumption rate. This star burns hydrogen millions of times faster than our sun. This means that every second, WOH G64 radiates an amount of energy equivalent to billions of hydrogen bombs detonating simultaneously. To put it into perspective, the total energy emitted by our sun over thousands of years, WOH G64, can generate in mere seconds. This intense release of energy creates a powerful radiation pressure from within the star, pushing material outward. This radiation pressure is so significant that it pushes WOH G64 close to the Eddington limit. This is a theoretical threshold where the outward radiation pressure from inside the star balances with the inward gravitational force. When a star reaches or exceeds the Eddington limit, it becomes highly unstable. The powerful light from WOH G64 doesn't just affect the planets within its cluster, but could also impact neighboring stars, creating complex interactions in the cosmic environment. Future supernova explosions from WOH G64 could generate shock waves, stimulating the formation of new stars in the surrounding regions. WOH G64, with its extraordinary brightness and massive size, lives in a delicate state of balance, where even the smallest change could lead to violent disturbances on its surface and within its structure. It's this instability that contributes to its immense size, as the outer layers of its atmosphere are pushed farther out. The star's burning power isn't just shown through its size, but also in its ability to affect the surrounding environment, opening new possibilities for the formation of new stars. If the immense power of WOH G64 is seen as a colossal nuclear reactor, then a haunting hypothetical question arises. What would happen if this energy machine, with its intense brightness and immense size, existed at a much closer distance? What if it replaced our sun at the center of our solar system? This scenario is not just a thought experiment in scientific thinking. It is a stark demonstration of the ferocity of supermassive celestial bodies. As mentioned earlier, if WOH G64 were to replace the Sun, it would engulf the inner planets, including Earth. However, let's assume a safer distance. Let's imagine Earth being shifted to a distance 500 times farther than our current Sun's position. Even then, Earth would still face a terrifying reality. Under the light of WOH G64, day would forever be a fiery red with no night. The sky would no longer be its familiar blue, but would turn into a deep, hellish red, dominated by the intense light and the characteristic spectrum of a red supergiant. This light would penetrate the atmosphere, tinting every landscape in red and completely altering our concept of daylight. The most horrifying consequence would be the global temperature and climate. With the immense energy WOH G64 emits, even at a distance of 500 AU, the temperature on Earth would rise to unimaginable levels. Studies show that a star as bright as WOH G64 could heat the atmosphere, alter its structure, and lead to extreme weather phenomena. Could life survive in such an environment, or would it be wiped out by the intense heat? Oceans would boil and evaporate within hours or days, turning our once blue planet into a barren desert. The atmosphere would be heated to the point where gas molecules would be ionized, creating a hostile environment incapable of sustaining life. The presence of WOH G64 could also affect the evolution of species on Earth. The intense light and radiation from this star could stimulate plant growth, but it could also have negative effects such as inducing genetic mutations. Studies on radiation from other stars have shown that ionizing radiation can increase mutation rates, affecting reproduction and the development of species. No form of life, from the smallest bacteria to the most complex organisms, could survive in such extreme temperatures and radiation. The protective ozone layer would be destroyed, exposing Earth's surface directly to harmful ultraviolet and X-rays. WOH G64, with its universe-burning power, serves as a reminder of the limits of life in the harshest environments of the universe, where existence is nothing more than an endless race against time. In stark contrast to the seemingly eternal appearance of the stars in the night sky, massive stars like WOH G64 live a brief life, a constant race against time. WOH G64, like all stars, was born from the gravitational collapse of enormous clouds of gas and dust in interstellar space. However, due to its immense mass, its formation process is much faster and more intense than that of smaller stars like our Sun. When a region of the gas cloud begins to contract, matter gathers and heats up enough to kickstart nuclear fusion. For stars with tens of times the mass of the Sun, this phase takes only a few million years to reach its maximum size and brightness. This is an incredibly short period on the cosmic scale, just a blink compared to the billions of years that average stars like our Sun exist, showing the astonishing urgency of their evolutionary process. It is precisely WOH G64's enormous mass and its insane rate of fuel consumption that determine its short life. To maintain enough pressure against its overwhelming gravitational pull, WOH G64 must burn nuclear fuel at an unimaginable rate. Its core consumes hydrogen and heavier elements at such speed that while it takes the Sun billions of years to consume a certain amount of hydrogen, WOH G64 can accomplish this feat in just a few thousand years. This rapid depletion of fuel means that its energy supply will run out in a relatively short time. WOH G64 is in a constant state of flux, undergoing highly volatile evolutionary phases. as it exhausts the hydrogen in its core, it begins to expand and cool, transforming into a red supergiant like WOH G64. This phase is often accompanied by internal instability and continuous fluctuations, resulting in massive eruptions of material into space, forming gas and dust halos surrounding the star. These fluctuations are not just signs of instability, they are evidence that the star is struggling to maintain balance before entering the final stage of its life. The short and intense life cycle of WOH G64 is not only a testament to the incredible diversity of stars in the universe, but also a powerful reminder of the relentless cycle of birth and death that governs everything in existence. When the last of its fuel is exhausted, the end of a massive star is not just a simple event, but a cosmic disaster of unimaginable destruction. It's the moment when the life of a giant star ends in a spectacular cosmic fireworks display, sowing the seeds for new beginnings and reshaping the structure of the surrounding space. Once WOH G64 has burned through elements from hydrogen to helium, helium to carbon and oxygen, and then silicon, its core will reach the final fusion stage, producing iron. Unlike previous fusion reactions that release energy to counteract gravity, iron nuclei require energy input instead of releasing it. This means the radiation pressure that keeps the star balanced vanishes in an instant, causing its own immense gravitational pull to become uncontested. With no outward pressure from fusion, the star's core collapses within seconds. The uncontrollable gravitational force will compress the material into an incredibly small space, causing the core to shrink from the size of Earth to just a few dozen kilometers, about the size of a large city. This collapse generates an extreme burst of energy, ejecting the outer layers of material at nearly the speed of light, creating a massive shock wave. It is this shock wave that causes the hypernova explosion. Unlike a regular supernova, a hypernova is an exceptionally powerful explosion that only occurs with stars that have an initial mass greater than 25 to 30 times the mass of the Sun, like WOH G64. This explosion would shine billions of times brighter than our Sun, outshining all other stars in the galaxy. The energy released in a hypernova could equal the total energy emitted by our Sun over its entire lifespan. The shock waves from the hypernova would destroy everything within a radius of tens of light years, sweeping away planets, asteroids, and clouds of gas and dust in its path. This is one of the most violent and destructive events in the universe. After the hypernova explosion, with the massive size of WOH G64, the remaining core will be too heavy to become a neutron star. Instead, it will continue collapsing, surpassing all physical limits, forming a massive black hole. Much like Stephenson 218, another red supergiant of similar size, WOH G64, is likely to end its life cycle by forming a black hole. A region of space-time where even light cannot escape, where familiar laws of physics are bent. The death of a giant star is not just a display of destruction, but also could be the catalyst for another terrifying cosmic phenomenon. Gamma-ray bursts, GRBs, are considered the highest energy events in the universe since the Big Bang. In just a few seconds or minutes, a gamma-ray burst releases as much energy as the sun will emit over its entire lifespan. These intense gamma rays are emitted by supernova explosions, especially hypernovae. Instead of spreading energy evenly throughout space, these gamma rays are concentrated into two narrow symmetrical beams, shooting out along the rotation axis of the collapsing star. They travel at incredible speeds, carrying enormous amounts of energy. Scientists classify GRBs into two main types based on their duration. Long GRBs, typically associated with the collapse of massive stars like WOH G64 into black holes, occur when the core collapses and creates a rapidly spinning accretion disk that ejects powerful beams of material. Short GRBs lasting less than 2 seconds are often caused by the merger of two neutron stars or a neutron star with a black hole. In the case of WOH G64, its death is very likely to produce a long GRB, a rare yet incredibly violent event. The most terrifying scenario is a potential apocalyptic scenario. If a gamma-ray burst from a GRB were close enough and aimed directly at Earth, the consequences would be catastrophic. Gamma rays are the most energetic form of electromagnetic radiation, capable of penetrating matter and triggering powerful chemical reactions in the atmosphere. In just seconds or minutes, this colossal burst of gamma rays would rapidly and completely destroy Earth's ozone layer. The ozone layer, located about 1530 km above the Earth's surface in the stratosphere, is the planet's natural shield, protecting us from harmful ultraviolet radiation from the sun. Once the ozone layer is destroyed, Earth's surface would be exposed to immense levels of ultraviolet radiation, hundreds, even thousands of times more intense than usual. The sudden surge in UV radiation would cause a mass extinction on a global scale. Plants, the foundation of the food chain, would be severely damaged or wiped out as their DNA is destroyed. Marine plankton would also be heavily impacted, disrupting the entire oceanic ecosystem. The sky could turn orange or red due to chemical reactions in the atmosphere, and surface temperatures might drop suddenly. For example, the Ordovician-Silurian extinction event, which wiped out approximately 85% of marine species, has been suggested by some scientists to be linked to a GRB from a star near the Milky Way. Although no direct evidence has been found, the possibility that a GRB could cause a global extinction event serves as a powerful reminder of the fragility of life in this ever-changing universe. Understanding extreme cosmic phenomena is crucial. The journey of exploring WOH G64 has taken us from staggering scales and destructive power to the legacies that shape life itself. Looking back at the entire story of this giant star, we realize a deeper message about the universe and our place within it. Supernovae and hypernovae, events that seem to bring nothing but destruction, are actually some of the greatest cosmic events in creation. They are where the building blocks for planets, water, and life itself are scattered across space. WOH G64, though terrifying, will ultimately contribute in an irreplaceable way to the material cycle of the galaxy, possibly sowing the seeds for a new generation of stars and planets somewhere in the distant future. The story of WOH G64 is also a powerful reminder of the fragility and grandeur of both humanity and the universe. We too are part of this grandeur, made from elements born from the deaths of colossal celestial bodies like what WOH G64. WOH G64 is not just a star. It is a symbol of the mystery and infinite power of the universe, challenging our imagination and driving humanity's unceasing desire to explore. We are still on the journey to uncover the deepest secrets of the cosmos. And with every new discovery, our awe for this greatness only grows. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.